A famous math problem that had gone unsolved for nearly 60 years might have finally been cracked. Today, I want to tell you the story of this problem, which begins in 1966 and take you all the way up to just now, when a student from Seoul, South Korea claims to have solved the problem in his thesis at University of Michigan. Part of what makes this problem so popular, as with many popular unsolved math problems, is that it's very easy to understand and has a sort of cute premise. I recently moved, and moving was a big fat pain. As part of my move, I was helping my roommate move his couch, and it didn't fit in the elevator, and so we had to bring it up 4 flights of stairs, and the couch was way bigger than it looks in this doodle. It was a big pain, as moving couches in 3-dimensional space often is. But today's math problem, although it is about moving couches, is not about moving couches in 3-dimensional space. It takes a far more simpler tact to the couch moving problem, and considers moving a couch down a 2-dimensional hallway which encounters a sharp 90-degree right turn. Obviously, if you're moving a couch, or a sofa as it's called in the literature, through this hallway, this turn is going to be the trickiest part, assuming there aren't any pits of lavas or pools of piranhas that you're going to have to hop over later down the line. Barring that, this is going to be the trickiest part, and depending on the size and shape of your sofa, it might not even be possible to bring it across this corner. Consider this rectangular sofa. You would move it, you'd get all the way up here, at which point, by the looks of things, you're just gonna be stuck. There's no way you're gonna be able to rotate that rectangular block sofa across the corner and then proceed down the rest of the hallway. So this sofa, as drawn, is simply too big. Of course, its shape doesn't work, it's too big, no dice here. On the other hand, obviously, some sofas could be moved across this sharp 90-degree right turn. For example, if you just had a very tiny square sofa, that would be straightforward enough to just move up and then move across. No problem at all. The area of this sofa would necessarily be pretty small, but it could definitely move across that 90-degree turn. It was in 1966 that mathematician Leo Moser posed this problem that would become known as the moving sofa problem. The problem is, what's the maximum area we can have for a sofa in this situation that is able to be navigated across the hallway? We're considering that this is a purely 2D situation, so you're not gonna do any sort of weird vertical twists and turns of the sofa. It's totally 2D. Now, I'm not a researcher at a university, right? I'm just a guy in his room with snacks, so I can't 3D print these things for you, but I can give you the best demonstration I know how with these cute connected blocks. So let's say this is our hallway, which has this sharp 90-degree turn. Certainly we know a small square sofa could be moved across this hallway, but we might as well make the square sofa as big as possible as, say, our first attempt at a solution to maximizing the sofa's area. So whatever the constant width of this hallway is, let's say its width is 1 unit. Then, a very easy starting solution to propose would be a square sofa that is 1 unit by 1 unit. So this isn't cut perfectly, it doesn't fit exactly in the hallway, but just imagine with me that this square perfectly fits in the width of the hallway. So this would be the biggest square shape we could move across the turn. You just move it up and over. You don't have to rotate it at all or anything. It's a very simple shape. And its area, of course, is just 1, because it's a square, 1 unit by 1 unit. Now, if we're trying to maximize area, the square sofa's area of 1 square unit is not very good, and it's very easy to do better. Consider a semicircle. Here's a semicircle, and again, let's suppose that its radius is 1 unit, so that it just fits perfectly snug in the hallway. Because we have a semicircle, we're able to get some extra area that we weren't able to get in the square, and because it's a semicircle, when we push it all the way to the end of that vertical slice here, where it then slams into the wall, we can do a simple rotation, whoop, just like that, and now it'll slide no problem down the rest of the hallway. Much of the literature about the moving sofa problem will also discuss the motion from the perspective of the hallway, where we imagine the sofa as being fixed, and that would look something like this. The hallway moves down, 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 and then it rotates, and then it slides across, just like that. Our square sofa had an area of 1. What about the area of our semicircle? Like we said, we are regarding its radius to be 1 unit, so its area would be half pi r squared, with r equal to 1. So the area of a full circle is just pi r squared. Since this is a semicircle, it will be 1/2 pi r squared. That, of course, is just half of pi, which is about 1.57. So that's a pretty good improvement over the square's area of just 1. But can we do even better than that? Take a minute and think about any alterations we might be able to make to the semicircle to get a bigger sofa around this pesky 90-degree corner. Our next improvement comes from a mathematician named John Hammersley. He proposed this sofa in 1968, so that's 2 years after the problem was originally posed by Leo Moser. Interestingly, this Hammersley sofa is actually starting to approach a shape a little bit more like a normal sofa, although it's even more like the shape of an old telephone. Let's see how this shape is able to navigate through the hallway. We'll go into the exact details of this shape in a minute, but the gist of it was to take the semicircle from before, cut it in half, and pull those 2 quarter circles apart, and then add as much sofa as you could in between the quarter circles. Naturally, a hole has to be left here to allow this longer shape to actually make the spin around that 90-degree corner. So this is going to go forward and bang right into that back wall pretty quickly because it is a long shape. You can see how its length compares to the semicircle. It is quite a bit longer. Now, because of that hole in the middle, it's able to complete a rotation across the corner, just like that, and then proceed, no problem, down the rest of the hallway. I'll just show you that beautiful motion one more time. We go down, and then we do a little bit of turn. I'll lift my hand up so you can start to see that turn. We turn, and bam, go right down, no problem. The exact construction of Hammersley's sofa is pretty simple. Like I said, it begins with taking that semicircle from before, which had radius 1, cutting it in half to get 2 quarter circles, and then separating them. So we have on the left and right side of Hammersley's sofa those 2 quarter circles of radius 1. This is of course not to scale, but just a sketch to help us calculate the area. So radius 1, radius 1, radius 1, radius 1. What's going on in between? Well, the idea is that we just attach a rectangle to these quarter circles in between, and then we cut out a semicircular slice so that we're able to make that turn. So this part of the sofa gets chopped out. But what exactly are the dimensions of this semicircle and this rectangle that connects the quarter circles? We would need to know those, of course, to find the area of this sofa. Obviously, the radius of these quarter circles is 1, so that it's able to fit perfectly in the hallway. But the radius of this semicircle we cut out could theoretically be anything between 0 and 1, that is. It can't exceed 1 because then it would go outside of the rectangle, which wouldn't make any sense. But what is this radius? Well, if we write an expression for the area of Hammersley's sofa with some radius r, it's pretty easy to use calculus to figure out what radius would maximize the area. If you don't know calculus, don't worry, this doesn't take much, it's mostly just basic geometry. So let's see, we're going to take an equation for the area of Hammersley's sofa. First, the area of the quarter circles is very straightforward. It's just 2 times the area of a single quarter circle. The area of a quarter circle is 1/4 the area of the whole circle. So 1/4 of pi r squared, where again, in this case, r, the radius, is 1. So this is the area of the 2 quarter circles. That's not going to change. Then we want to add the area of this rectangle that's between them and take out the area of the semicircle that we are cutting. The area of the rectangle is just length times width, and the length is 2 times the radius of the semicircle. That's a radius, that's a radius, so the length of the rectangle is 2 times the radius. On the other hand, the width is just a radius of the quarter circle, which of course is 1, so this is getting multiplied by 1. So that's the area of the rectangle. Then we need to subtract the area of the semicircle, which gets cut out of it. Of course, the area of a semicircle is 1/2 the area of the whole circle, so 1/2 pi r squared. Then just doing a little bit of simplification here, 2 times a fourth is a half, 1 squared is just 1, so this is pi over 2 on the far left, that's 1/2 pi. And then we have that plus 2r and minus pi over 2r squared. So with basic geometry, that's an expression for the area of Hammersley's sofa based on our chosen radius for that semicircle that we cut out. We can then use calculus to find the best choice for r. If we were to graph this equation, we would get a downwards facing parabola. And so we're looking for the value of r that puts us right there at the top. That's the maximum area. To find that, we need to find where the tangent line to that parabola is horizontal. That means there's a slope of 0. And we do that with calculus. When we take the derivative of the area, which is written a prime, we get the slope of the lines that are tangent to this parabola. Tangent lines look like that. They just grace or just kiss the curve. Now every calculus student will know that to take this derivative, we just have to use the power rule on each term. The derivative of pi over 2 is 0, the derivative of 2r is 2, and the derivative of negative pi over 2r squared is negative pi r. Like we said, the derivative gives us the slope of the tangent lines. We want the slope to be 0 to find that maximum point, so we'll say that a prime is 0, and then we just have to solve this equation for r, the radius, which is straightforward. We'll add pi r to both sides, which gives us pi r equals 2, and then divide both sides by pi. So we find the radius we're looking for is 2 over pi. That's going to maximize the area of Hammersley's sofa. And so of course, when Hammersley proposed this sofa as a potential solution to the problem, this is exactly the radius he used, 2 over pi, which if you plug it into this area equation, gives us a very cute area for the sofa of pi over 2 plus 2 over pi, which if you run the numbers is about 2.2074. So another pretty darn good improvement. Now in trying to find the biggest sofa that will fit down the hallway, note that each sofa that does fit down the hallway can act as a lower bound. So Hammersley had this now established as a pretty big lower bound for whatever that maximum area happens to be. If we agree to call the maximum area alpha, Hammersley's sofa tells us that alpha must be at least 2.2074. Perhaps that's the biggest we could get the sofa, we don't know, but certainly we can get the sofa at least that big. But on top of presenting the sofa to establish a lower bound, Hammersley also established an upper bound of 2 times the square root of 2, which is about 2.83. So at this point, we know the biggest sofa that we can fit down the hallway is at least this big and no bigger than 2.83. Pretty narrow set of possibilities. But can we do even better than Hammersley's sofa? Can we fit a bigger sofa down that hallway? Well, it wouldn't be for another 24 years. That puts us in 1992, when a mathematician named Joseph Gerver finally proposed what was for a while the long-standing best potential solution. Gerver's sofa is considerably more complicated than Hammersley's sofa, so we're not going to go through any in-depth calculations of its area, but it was a small improvement over Hammersley's sofa. His being Gerver's, had an area of about 2.2195. This decimal could continue, but those are the first few digits. So unlike with Hammersley's sofa, which had this very cute exact expression for its area, there is no such simple expression for the exact area of Gerver's sofa. So just how complicated is this sofa? Well, of course, we know that Hammersley's sofa was made up out of, we might say, 4 parts. 2 quarter circles and 1 rectangle that had 1 semicircle cut out of it. So 4 parts. So then how many parts are Gerver's sofa, which is just a little bit bigger, made up of? Well, it turns out it is made up of 18 parts, and it looks like that. And it is possible you're thinking, wait a minute, that's just Hammersley's sofa. Well, no it isn't. Now, partly it's because I cut it with scissors that it looks so similar. These aren't exact 3D prints, but secondly, they do just look very very similar. It is, of course, a very small improvement, but it is an improvement nonetheless. It is a little bit more bulbous around the edges here as compared to Hammersley's sofa. It also has softer corners here in the inside cut. This inside cut is also made of a few different parts. It's not just a semicircle. So this takes a lot more work to describe exactly. Here is a bigger printout of the two sofas that hasn't been sullied by the cutting of my scissors, and you can see the separate parts of Gerver's sofa indicated by the tick marks on this picture. Gerver's sofa, of course, contains a few straight lines, but it also contains circular arcs and involutes of circles and involutes of involutes. Now, if you're wondering what an involute of a circle is, it's created by wrapping a taut string across a circle and sketching out the tip of the string, the curve that traces. This picture does a decent job of showing that. So you have a circle, and then here's a string pulled taut that is attached to the circle, and then as we wrap the string around the circle, imagine tracing out the tip of the string's path. That is an involute of the circle. So you could imagine that we have a very tiny squid which is ejecting ink on the tip of this thread, and there it is like that, and I just pull it across the circle and it's tracing out, the curve. It's not a great demonstration, but I think you get the picture. Of course, an involute of a circle would be the same thing, except now we're attaching a string to the involute and then wrapping the string around the involute and tracing out the tip of that string. After 1992 then, the big question was, is Gerver's sofa the optimal solution to the problem? Or is it possible to construct an even bigger sofa that can get through this hallway? At this point, of course, again using alpha to represent the maximum area sofa that can fit across the hallway, with Gerver's sofa, we now knew that alpha was at least 2.2195, just rounding off at 4 digits. And in 2018, Yoav Kalis and Dan Romick, who appeared in the famous number file video on this problem, further lowered the upper bound to about 2.37. So again, that was in 2018. They took a more discrete and hallway-centric approach to the problem, imagining the hallway moving around the sofa in a discrete sequence of steps. But still, in 2018, the problem was unsolved. Now, Gerver had some arguments supporting his sofa, in fact, being the optimal solution, and many people thought that indeed it would be. The optimality of Gerver's sofa was further supported by Xipeng Dang, who published a paper in July of this year, 2024. He approached this problem using the calculus of variations. He treated the area of the sofa as what's called a functional. Representing the sofa area as a functional on a set of parametric equations for the rotation path, he then used the Euler-Lagrange equations to optimize this area. And his calculations got into a sofa with a maximum area that seemed to be approaching Gerver's sofa. In fact, the area he calculated was off when compared to the area of Gerver's sofa by less than 4 times 10 to the negative 8. So his calculations certainly supported Gerver's sofa as being the sofa of maximum area. At this point, it had been over 50 years since the moving sofa problem was originally posed. Still, nobody had quite solved it. Now, some people thought that Gerver's sofa would in fact not be the optimal solution. In some ways, it seems a little unintuitive that such a peculiar sofa, constructed of 18 separate parts, would be the ideal solution. Surely, for something so complicated, there could be some small alterations that could be made in sofa design to get something a little bit bigger across that hallway. But then finally, Jineon Baek, December 2nd, 2024, might have finally put the nail in the coffin for this problem with his thesis, a 119-page paper claiming to prove once and for all the optimality of Gerver's sofa. And you can read his 119-page paper now on archive.org. work, link in the description. Now, of course, many intelligent mathematicians worked with and advised Baek to some degree that we don't know while he worked on this paper, including Dan Romick, who has previously published on this problem. So whether or not his solution is fully correct remains to be seen. We'll have to wait and see if the mathematical community as a whole agrees that all the details check out, but there's certainly great confidence that this might finally be it. Now, of course, Baek's paper, being a PhD thesis on a really difficult problem, is extremely complicated. If you don't have a background in math, you can get a taste of how complicated it is just with the very simple details in the introduction, and if you do have a mathematical background, you will not be surprised by the fact that the paper, of course, begins with defining the key terms. For starters, we have to define what a hallway is, and this is the definition used. The hallway L is taken to be the union of this horizontal strip HL, which is this Cartesian product between intervals, unioned with this vertical strip of the hallway, which is this Cartesian product between intervals. After this, of course, the definition of a moving sofa must be given. A moving sofa S is any translation of a non-empty connected enclosed subset of HL, that means the sofa starts in the horizontal strip of the hallway, that can be moved inside L, so we have to remain in the hallway. It can be moved inside L by a continuous rigid motion to a subset of VL, the vertical strip. So while I've been showing you the hallway like this, Baek's paper frames the hallway like this. So we move the sofa from a horizontal part to the vertical part. And from these simple definitions, the paper quickly gets quite complicated, though the entire first chapter is dedicated to giving overviews of the following chapters. It's a very thorough and well-written paper. As a whole, I understand the thing about as well as I understand women, but let me try to give you a gist of the final arguments that Baek makes for the optimality of Gerver's sofa. The argument comes down to considering any moving sofa S, and then enclosing it in a region that we'll call R. So this is my poorly drawn moving sofa S, and then Baek encloses it in this region called R. Maybe the region looks something like that, it's just a little bit bigger than S, and that's called R. Now he describes a manner in which any moving sofa S may be enclosed by some region R, and then we say that Q of S is the area of R. So R isn't just a single region, it is in particular a region corresponding to any moving sofa. It is like a function on moving sofas. Each moving sofa has an enclosing region R, which has an area, which is called Q of S. As a result of Q of S being the area of regions R that enclose moving sofas S, necessarily Q of S is an upper bound on the maximum area for a moving sofa. From there, two key things are proven: that Q of S is concave, and that Q of S has a local optimum, or a local maximum, when S, the moving sofa, is Gerver's sofa. So we may describe that as a local optimum at G, when S, the sofa, happens to be Gerver's sofa. There is a local optimum. Now, what is meant by local optimum? Well, it's not a global optimum, which is what we're looking for. For example, in this curve, right here, there is a local maximum, but it's not what we would call a global maximum, because there is somewhere else on the curve that is higher up. However, Q of S is shown to be concave. A concave function, for example, looks like this. It can't make another turn like this does to get an additional maximum. Hence, a local optimum of a concave function must necessarily also be global. Thus, in combination, these two properties, that Q of S is concave and has a local optimum at G, establishes that there is in fact a global optimum at G. In this case, of course, an optimum is a maximum. We're trying to maximize the area of the moving sofa. But this doesn't quite settle things yet. Just because Q of S has a local optimum at Gerver's sofa doesn't mean that Gerver's sofa is the optimum. However, this is just because there's a detail I didn't tell you yet. This enclosing region R was defined so that R actually is equal to S in the specific case when S equals G. This region R enclosing moving moving sofas will in fact exactly equal the region of the moving sofa if the moving sofa is Gerver's sofa. Hence, this local maximum, which we know to be a global maximum, that Q of S has at Gerver's sofa isn't just some theoretical upper bound that Q of S takes on, but is in fact exactly the area of Gerver's sofa. That is the global maximum. That is the optimum solution to the moving sofa problem. Again, if R was not constructed in this way, so that R equals S when S is Gerver's sofa, then Q of G, that is the area of the region that encloses Gerver's sofa, could just be the area of some region that maybe doesn't move through the hallway. It would just be an upper bound. But in fact, because of how it's constructed, we know that it is precisely the area of Gerver's sofa, which we know can move through the hallway. That's just my rough attempt at explaining the gist of Baek's math, which I can't come close to completely understanding. So please do correct my summary if you can down in the comments. But anyhow, that's the story of the moving sofa problem and how it might have finally been solved nearly 60 years after it was originally posed. Let me know what you think will end up becoming of Baek's paper. Will it be verified by the mathematical community once people have had a lot of time to look at it and go through the details? Or will there be a small hole that needs to be fixed? Or maybe a big hole that won't be fixed for some time to come? And hey, if you enjoyed this video, consider supporting Wrath of Math by joining as a channel member. You can get early and exclusive access to additional videos and lots of original music. I'll sing my heart out for you if you'll let me. Let me know in the comments if you have any questions, and be sure to subscribe for the swankiest math videos on the internet.
From my fate, twisting to escape this. Cutting out my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not infinite if you ain't listening. Not infinite if you ain't really